Hello everyone. Now I am going to present our machine learning project, which is LSTM based soft sensor for estimating nitrate concentration in aquaponics farming. Our project guide is Dr. Sri KRISHNA KARRI, and our team members are Savda Rakesh Reddy, myself Manikanta Ramkumar Pandalani, and Pedda Prolu Pavan. Next, I am going to introduce our project. In aquaponics monitoring, nitrate level is crucial for aquatic and plant well-being. Traditional methods are costly and time-consuming. To address this, an LSTM-based soft sensor was developed. LSTM effectively modes nitrate concentration and changes the aquaponics, achieving a remarkable MSE of 0.0074 and an squared score of 0.98. This solution holds potential for commercial applications, benefiting aquaponics operations, supporting researches, and enhancing sustainability. Coming to problem statement, aquaponics integrate growing plants without soil technology with aquaculture, having an important role in recovery of nutrients from effluents. Develop a method for accurate and real-time monitoring of nitrate concentration in aquaponic systems. The monitoring of nitrogen content in aquaponics relies heavily on human judgment, which can be subjective and lead to suboptimal harvest. This project proposes an LSTM-based soft sensor to address this issue by leveraging deep learning techniques to analyze sensors data and estimate nitrate levels in real time. Coming to dataset, the enclosed datasets are generated from freshwater aquaponics catfish ponds. The datasets are generated automatically at 5 seconds interval using the following water quality sensors driven by ESP32 microcontroller, dollars investment temperature sensor, DF robot turbidity sensor, DF robot dissolved oxygen sensor, DF robot pH sensor, which is V2.2, MQ137 ammonia sensor, and MQ137 nitrate sensor. The project is founded by the Laukuna Award for Agriculture in Sub-Sahara Africa 2020 under the management of the Meridian Institute, Colorado, USA. The dataset and results in the section were sensor readings for June to mid-October 2021. There are 12 datasets, each from 12 aquaponics catfish ponds. Each of the 12 ponds IoT unit has 6 sensors, which is temperature, turbidity, dissolved oxygen, pH, ammonia, and nitrate. As of the time of the report, each unit has generated over 17,000 instances. The datasets are downloaded at intervals, cleaned, and labeled.
My name is Pawan. My roll number is 521211. I'm going to present now LSTM architecture. A long short-term memory network usually just called LSTMs. There are four gates in LSTM: input gate, forget gate, store gate, put gate. The first step in our LSTM is to decide what information we are going to throw away from the cell state. The decision is made by the sigmoid layer called forgot gate layer. It looks at HT-1 and XT and gives output number between 0 and 1. For each number in the cell state CT-1, 1 represents the completely keep it, while 0 represents completely get forgotten. It's now time to update the old cell state CT-1 into the new cell state CT. We multiply the old state by FT, then we add it to CT. This is the new value scaled by how much we decided to update each state. LSTMs are capable of long-term dependencies. Now, model building. An LSTM neural network models was constructed using Keras with a TensorFlow backend. The model architecture included multiple bidirectional LSTM layers with dropout regulation. Swiss activation function was used to introduce non-linearity in the model. We have six hidden layers in the model, and one optimizer called a NADAM optimizer, and one loss function called mean square error. Now coming to data processing. The data sets we are using in this model undergoes extensive processing steps, which includes handling massive values, scaling features, removing outliers, and correcting column names. Future engineering techniques such as data transformation and outlier removal were applied to enhance the quality of the
On. Hello, I am Sawad Rakesh Reddy, roll number 521236. Now we'll explain about bidirectional LSTM. By-LSTM, bidirectional long short-term memory, is a recurrent neural network that processes sequential data in both forward and backward directions. It combines the power of LSTM with bidirectional processing, allowing the model to capture both past and future context of the input sequence. It has two passes. Forward pass. During the forward pass, the input sequence is fed into the forward LSTM layer from the first step to the last. At each timestamp, the forward LSTM computes its hidden state and updates its memory cell based on the current input and the previous hidden state and memory cell. Backward pass. Simultaneously, the input sequence is also fed into the backward LSTM layer in reverse order, from the last step to the first. Similar to the forward pass, the backward LSTM computes its hidden state and updates its memory cell based on the correct input and previous hidden state and memory cell, combining forward and backward states. Once the forward and backward passes are complete, the hidden states from LSTM layers are combined at each time step. This combination can be as simple as concatenating the hidden states or applying some other transformation. Now we will look at the pros and cons of using bidirectional LSTM. The pros are it captures long-term dependencies, improves performance, and it is a flexible architecture. Cons are it has high computational cost, requires large amount of data, and difficult to interpret.
Now we are going to explain our code. My name is Pawan, roll number 521211. Now I am going to explain a pre-processing of our code. These are the libraries we imported for our model, Pandas, NumPy, and TensorFlow. These are the 8 datasets we used for our model, which contains the information about ponds and their environment for fish growth. This dataset contains the information about created date, entry ID, temperature, NTU, dissolved oxygen, pH, ammonia, nitrate, uh, population, fish length, fish weight. If there are non-numerical values, they are converted into a null value. These null values are going to be replaced with mean values, missing data, imputation, concatenating data sets. Data sets are we are merging these data sets into single data set. Data.info gives us the information about the all data sets if all data sets null values. If there are null values, this data set gives there are null values, but there are no null values in this, so zero non-null values. Non-null value. Dropping unnecessary columns. There are some unnecessary columns in the data sets like create rate and entry data. Now we are going to drop that unwanted columns. Handling column mismatch, dropping redundant column, and correction column names. There are many column names in each data set. So we are assigning a single name for single name for each parameter of the data sets. Like temperature C. In each data set, there are different temperature C. So we are assigning single temperature C for all temperature C's in the all data sets. Data dot is null dot sum. This gives total number of null values in the data set. If null values are there, the null values are going to be replaced by mean values. Handling infinite values and filling missing values with column means. If there are any infinite values and missing values, they are replaced with mean values. Handling negative values in specific columns. Uh, if there are negative values in the given data set, they are going to be replaced by mean values. Visualizing a box plots of water quantity features. Now we are plotting the data set values in a box plot of water quality features with parameters, temperature, NTU, and other parameters.
Hello everyone, I am RAKESH 521236. Now I am going to explain about removing outliers using Z-score. For this, first we will plot the data points in a Gaussian distribution using Z-score. Z-score equal to x minus mean by standard deviation. We have kept the threshold as 3. The values lying in threshold will store it in data, and we will check the mean, standard deviation, minimum, percentiles and maximum of the following data. It shows that minimum temperature is 21 and maximum is 27.5 degrees Celsius. We'll transform the nitrate data into np dot square root of nitrate. We'll check the shape of the data. It is 9,48,004. We'll scale the data using min-max scalar to 0 to 1, and we'll observe the distribution of the data points using a box plot. And now we will build the LSTM model. For this we will import the necessary libraries first. As our main aim is to calculate nitrate, we'll drop the nitrate value from x and take all other parameters. For y we will take nitrate. First we will split the data into train and test sets using train test split. Test size equal to 0.2. We'll scale the data using standard scalar. We'll reshape the data for the LSTM and features equal to x underscore train underscore scale dot shape 1. Now we will build the LSTM model. For this we will call sequential model first. Our first layer is bidirectional LSTM with 512 units, activation as tan H and recurrent activation as sigmoid. And we will have a dropout layer 0.2 to avoid overfitting. And we will have a third layer, bidirectional layer LSTM 256 units, activation tan H, recurrent activation sigmoid, and dropout layer 0.2. And another layer LSTM 128 units, activation tan H, recurrent activation sigmoid, and dropout layer 0.2, dense 256, activation tan H. As we have only a parameter of calculating nitrogen, will have only one unit, that is dense 1. Now we'll compile the data using NADM optimizer and loss as mean square error. Mean square error is 1 by n y minus y hat whole square. We'll train the model using model.fit with 5 approaches and batch size 32. We'll predict the model using model.predict. We'll calculate the mean square error between y test and y prediction. After running the code for 5 approaches, we have got mean square error 0.004, which is very less. We will evaluate the LSTM SS model performance. We will calculate mean square error R2 score, mean absolute error, and we'll check the learning parameters. We got mean square error 0.004, R square score is 0.9, and which shows high correlation between predicted and actual values. Now we will check the shape and parameters of the layers.
Hello everyone, myself Manikanta Kumar. My roll number is 521209. Now I'm going to explain the sequential model. Coming to the bidirectional layer, the output shape is none, 1 and 1024. and the learning parameters are 2, 1, 3, 4, 0, 1, 6. In the dropout layer, there are no learning parameters, and the shape is none, 1, and again 1024. And bidirectional layer, it is again the output shape is none, 1, and 512, and the output learning parameters are 2, 6, 2, 3, 4, 8, 8, and the dropout 1 parameters layer, the output shape is none, 1, and 512, and there are no learning parameters, and the IS. Coming to LSTM2 layer, the learning parameters are 328, 129, and the dropout 2 layer, the learning parameters are 0, and the dense layer, the learning parameters are 33024, and the dense 1 layer, the learning parameters are 257. Coming to total parameters, it is 15356,934, and the transial parameters, it is there are 5118977, and the non-transial parameters 0, and the optimizer parameters, there are 10237957. Heading చదివే. Now coming to visualizing actual versus predicted nitrate concentration. We will visualize the plots between actual and predicted nitrate concentration. We will plot y test on x-axis and y predicted on y-axis, and plot a graph which shows that predicted value is almost similar to the actual value. Coming to the graph, actually the blue one is indicated with actual value, and the red one is indicated with predicted value. Now coming to another graph, which is actual versus predicted nitrate concentration. This is another graph which the samples are 1000 samples, and coming to this graph is per 2000 samples. Next. uh, Now coming to another plot. This is the scattered plot of actual versus predicted nitrate concentration. The values are almost same, which is highly correlated. Now coming to the error distribution plot. Here x minimum is equal to minus 0.5 and x maximum is equal to 0.5, and error is equal to y test values minus y predicted values. Now we can see the error distribution plot. We can see the error is almost 0. Now coming to the residues plot, actual versus predicted. Here also we can see the error is almost 0 as we predicted. Coming to model training and evaluation, the model was trained on the pre-processed data for 5 approaches with NADM, optimizer, and mean squared error loss function. The evaluation metrics, including mean square error, R squared score, and mean absolute error, were calculated to assess model performance. Visualizations such as line plots, scatter plots, and histograms were employed to analyze model predictions, error distribution, and residuals. Next, going to the conclusion, the LSTM model demonstrated promising performance in predicting nitrate concentration based on water quality features. Evaluation metrics indicated satisfactory model accuracy and reliability. Further optimization and fine tuning of the model could potentially enhance its predictive capabilities and adaptability in real world scenarios. The references we have taken are from the research papers. The estimating fish weight growth in aquaponic farming through machine learning techniques, and also the evaluation of nitrate level in green lecture conventional growth under natural conditions and aquaponic system. And thanksgiving to the project guide, our Dr. Sri Panikrishna sir, and our team members, Savda Rakesh Reddy and myself and Pawan. Thank you.